everyone, thank you so much for clicking onto the video. Today we're going to be learning about weak acids and bases Ka for weak acids. So here are our learning objectives. The first is to know that weak acids and bases dissociate only slightly in aqueous solution. And then we're going to learn about the dissociation constant Ka and its relationship with pKa. So we're going to construct an expression for Ka and perform calculations relating the pH of a weak acid the concentration of the acid and the dissociation constant Ka, and how to convert Ka into pKa and vice versa. Now we're going to look at another constant, which is the dissociation constant. So weak acids and weak bases only dissociate slightly in aqueous solution, which means that an equilibrium is set up. And Ka is the dissociation constant for a weak acid. So in this equilibrium, the weak acid is the Ha. We've given it a general formula, so it's got a H for the H plus ion. And so that acts as the acid, and water acts as the base. Now thinking about equilibrium constants, we can find the Kc of this equilibrium. And we have that Kc is equal to the concentration of the products at equilibrium divided by the concentration of the reactants at equilibrium. And so the Kc for this reaction would be equal to the concentration of A minus multiplied by the concentration of H3O plus divided by the concentration of Ha multiplied by the concentration of H2O. Now the concentration of H2O is again a constant, like it was when we were trying to work out the ionic product of water. And so that goes into the constant. And so rearranging this, we get Kc multiplied by the concentration of water is equal to the concentration of A minus multiplied by the concentration of this H3O plus ion and divided by the concentration of Ha. And this new constant that we formed is what we call the dissociation constant. This is Ka, and this is the dissociation constant, and this is for the weak acid, so for Ha. So we have Ka is equal to the concentration of A minus multiplied by the concentration of H3O plus, all divided by the concentration of Ha. So for example, if we had this equation, if we had ethanoic acid added with water and an equilibrium was set up to form this CH3COO minus ion and H3O plus ion, then we could find the Ka by doing the concentration of CH3COO minus multiplied by the concentration of H3O plus divided by the concentration of the ethanoic acid. So how do we interpret the value of the Ka? Well, if we think back to the formula of Ka, so we've got the concentration of A minus multiplied by the concentration of H3O plus over the concentration of Ha. So this is for the equation of adding Ha with water to form this equilibrium where we have the H3O plus ions and A minus ions. Well, that means that if we have quite a large value for this concentration of Ha, so if we have a high concentration of Ha, that means that this Ka value will be quite small. And if we looked at having a low concentration of Ha, then the Ka would have a big value. And so now let's look at the equation that we have. So in the first scenario where we have a big Ha, that means that the acid hasn't dissociated that much because it hasn't been able to give loads of protons away. And so that means that when the Ka is small, we have a weak acid. So it's not protonated as easily. So it doesn't give away that proton as easily. And when we have a low concentration of HA, that means that the forward reaction has been very, very successful and protons have been given away. And so it is a bit of a stronger acid. We can choose to quote something called the pKa value instead of a Ka value of an acid. And so we have this expression, pKa is equal to minus log to the base 10 of Ka, where Ka is the dissociation constant. And that's of the acid. And so to get Ka in terms of pKa, you would have to do Ka is equal to 10 to the power of minus pKa. And so from this, we can see that if we have a very strong acid, stronger acids have a larger Ka value, as we've learned. And because they have a larger Ka value, that means they need to have a smaller pKa value. And that's because looking at this here, if the pKa is very, very large, then this 10 to the minus of a very, very large number would mean that this Ka would tend to 0. So it'd get closer and closer to 0 as the pKa got bigger and bigger and bigger. And so that means that if you want a large Ka value, so not tending towards 0, we need a small pKa. So stronger acids have a larger Ka value and a smaller pKa value. So we can actually relate the pKa value and the pH. So if we think back to pKa, we have the formula pKa is equal to minus log 10 of Ka. And so using our formula for Ka, we then have pKa is equal to minus log to the base 10 of the concentration of H plus multiplied by the concentration of A minus over the concentration of HA, the acid. And so using laws of logs, we then have the pKa is equal to minus the log to the base 10 of this H plus the log to the base 10 of the concentration of A minus over the concentration of HA. And then what we get is we get that this is actually equal to pKa equals, because we have this minus log 10 here of H plus ions, this is equal to the pH, because that's the equation that we've learned. And then this is minus log to the base 10 of the concentration of A minus of our HA, which is the acid. And so we've got this formula here of pKa equals pH minus log 10 of the concentration of A minus over the concentration of HA. And some really important things about this is that when this minus log to the base of 10 of this concentration of A minus over the concentration of HA, when this is equal to 0, then we have pKa equals the pH. And for anything, for any log, well, a natural log, to equal 0, the inside of this bracket would have to equal 1. for the log 10 of this thing to equal 0. And when the concentration of A minus over the concentration of HA equals 1, we call this the half neutralization point. And so the acid is exactly 50% dissociated. So this is when the acid is 50% dissociated. And we call this half neutralized. And that's because we've got the same amount of the acid which has gone through the equilibrium and this A minus. So if we look back to the equation of HA plus H2O goes to form this A minus and the HCO plus ion, if we've got the same concentration of this A minus and this HA, that means that the equilibrium has gone halfway because we've got the same amount of each. Now we're going to try and calculate the pH of a weak acid. The first point is that we can't assume that the concentration of the acid equals the concentration of H plus, like we did for strong acids. And this is because weak acids don't undergo complete dissociation. And therefore, we need to use the Ka value to help us find the pH. So looking at this example, a sample of methanoic acid has a concentration of 0.01 moles per decimeters cubed. Its Ka value is 1.6 times 10 to the minus 4 moles per decimeters cubed. Calculate its pH. So the first thing we do is write out the equation. So we would have methanoic acid, which has a chemical formula of HCOOH, and then it would be in equilibrium with its HCOO minus ion and a H plus ion. And so to work out the Ka, we would have the concentration of HCOO minus multiplied by the concentration of H plus over the concentration of HCOOH. Now, a really important thing to remember is that at equilibrium, the concentration of the HCOOH and the H plus should be the same. And so we get that at equilibrium, the concentration of HCOO minus and the concentration of the H plus are equal. And that's because they're in a one-to-one ratio. And if you think back to working out equilibrium moles, then you'll see that the concentration of this negative ion and this concentration of the H plus ion are equal at equilibrium. And so this means that our Ka equation at equilibrium becomes Ka equals the concentration of H plus squared over this HCOOH. And so we can work out this concentration of HCOOH at equilibrium by doing this. So we have this HCOOH at equilibrium that we're trying to find. And then this is actually equal to the concentration it was at the beginning. So let's denote this by concentration with a little I, so I standing for initial. And then minus this concentration of H plus at equilibrium. And so how we think about this is like we did with equilibrium moles. So to get the concentration of something that we don't know at the end, we have to use the ratios between the different species and then try and work it out. And so we have this equation of the concentration at equilibrium of this methanoic acid is equal to its original concentration minus the concentration of H pluses at equilibrium, because it's a one-to-one relationship. And so we can use the 0.01 that they gave us in the question, because that was the original concentration of methanoic acid. So we've got 0.01 minus the concentration of H plus at equilibrium. And as H plus is small for a weak acid, we can assume that the concentration of this methanoic acid at equilibrium is 0.01, because this is so small. So we say that this is very small for a weak acid, because it's not weak acids aren't completely dissociated, and so the concentration of H plus ions will be really small at equilibrium. And so we can assume that this concentration of methanoic acid at equilibrium is equal to 0.01. And so now, rearranging our equation for the Ka, we will be able to find the concentration of H plus ions in order to find the pH. So we have, we're just going to rearrange this. So we get that the concentration of H plus ions is equal to the square root of Ka multiplied by the concentration of this methanoic acid at equilibrium. And so we get the concentration of H pluses is equal to the square root of Ka, which was 1.6 times 10 to the minus 4, multiplied by 0.01. And this comes out to be 1.26 times 10 to the minus 3 moles per decimeters cubed. And then we use the pH equation that we know. So pH equals minus log to the base 10 of the H plus concentration, and that equals the minus log to the base 10 of 1.26 times 10 to the minus 3, and so this comes out to be 2.90. So we can actually calculate the Ka value from the pH by doing a sort of backwards method to when we worked out the pH from the Ka value. So we're going to look at an example. The pH of a 1.67 times 10 to the minus 3 moles per decimeters cubed solution of ethanoic acid is 4.54 at 25 degrees. Calculate its Ka value. So what we do first this time is we work with the pH equation. So we have that pH is equal to minus log to the base 10 of the concentration of H plus ions. And so we can work out the concentration of H plus ions because we know this pH here of 4.54. And so rearranging this equation, we get concentration of H plus ions is equal to 10 to the power of minus pH. And in this case, it's equal to 10 to the power of minus 4.54. And that gives us 2.88 times 10 to the minus 5 moles per decimeters cubed. So now we write out the equation of the reaction that's happening. So we have ethanoic acid, which has a formula of CH3COOH. And then this is in equilibrium with its dissociated ions, so CH3COO minus and H plus. And so that means that writing out the equation for Ka, we have Ka is equal to the concentration of CH3COO minus ions multiplied by the concentration of H plus ions divided by the concentration of the ethanoic acid. And now we use the fact that at equilibrium, the concentration of both the ions will be equal. And so we get the Ka is equal to the concentration of H plus squared over the concentration of the ethanoic acid. And this is because these two concentrations of the ions are equal at equilibrium. And now we have to work out this bit, the concentration of the ethanoic acid. And so what we have is we have that the concentration of ethanoic acid at equilibrium is equal to its initial concentration. So again, we denote it with a little I, and minus this concentration of the H plus at equilibrium, because it's a one-to-one relationship again. And so what we get is we get that this is equal to the original, which is given in the question. So that is 1.67 times 10 to the minus 3. And then we assume that this concentration of H plus at equilibrium is very, very small because it's a weak acid. And so this is kind of like 0. So we take the concentration of this ethanoic acid at equilibrium as the original, so 1.67 times 10 to the minus 3. And now we can work out the Ka. So now we have that Ka is equal to, so writing out the equation again, we've got H plus squared over the ethanoic acid. And so we have 2.88 times 10 to the minus 5 all squared, and then that's divided by 1.67 times 10 to the minus 3. And this gives us 5.06 times 10 to the minus 7 moles per decimeters cubed. So before I move on to question 2, feel free to click off the video and try it for yourself first. So for A, write an expression for the acid dissociation constant Ka for ethanoic acid. So first what we do is write out the equation of ethanoic acid dissociating. So we have ethanoic acid, and this dissociates into the ethanoic ion and a H plus ion. And so we can find the Ka by doing the concentration of CH3COO minus multiplied by the concentration of H plus over the concentration of CH3COOH. And then for B, the value of Ka for ethanoic acid is 1.7 times 10 to the minus 5 moles per decimeters cubed. Calculate the concentration of ethanoic acid in a solution of the acid that has a pH of 2.69. So what we do here is we work with the pH equation first. So we have pH is equal to minus log to the base 10 of the concentration of H plus ions. And so in order to find the concentration of H plus ions, we need to rearrange this equation. And so we get the concentration of H plus ions is equal to 10 to the power of minus pH. And so for this experiment, we have the concentration of H plus is equal to 10 to the power of minus 2.69, and this is equal to 2.042 times 10 to the minus 3 moles per decimeters cubed. And so what we do now is we think about the Ka. So we've got this formula for the Ka, which is a concentration of CH3COO minus multiplied by the concentration of H plus over the concentration of the ethanoic acid. And the thing to remember is that because it's a weak acid, we assume that the concentration of H plus and the concentration of CH3COO minus is the same. And so what we get is we get Ka is equal to the concentration of H plus squared over the concentration of CH3COOH. And what we also need to remember is that because the ethanoic acid is a weak acid, it doesn't completely dissociate. And so the concentration of the ethanoic acid used in this formula for the Ka is the one for equilibrium. But this is actually the same as the one we initially start with, because the concentration of ethanoic acid at equilibrium is equal to the concentration of it originally minus the concentration of H plus ions added, of H plus ions formed, because it's a 1-to-1 ratio. But because it doesn't dissociate completely, we assume that this is very close to 0. And so we have that this equilibrium concentration of the ethanoic acid is very similar to the initial. And so now what we do is, so the value of Ka is 1.75 times 10 to the minus 5. So we use that in the equation, and we rearrange this Ka equation to find this concentration of ethanoic acid, which should be the same as the original. And so the concentration of ethanoic acid is equal to concentration of H plus squared over the Ka. And so we have that is equal to 2.042 times 10 to the minus 3 squared over 1.75 times 10 to the minus 5, 0.238 moles per decimeters cubed.